welcome back to Maths with Mr. Hammer. In this video we're going to be looking at graphing cubics. So here's the general function for a cubic. It's y equals ax to the power 3 plus b x squared plus c x plus d. And if we graph it, the general sort of look of this is going to be something along those sort of lines. And we also know that we can express this in factorized form. As we've shown in the last videos, there will be sort of three factors which you can put into brackets. So let's actually plot some of these. So here we go. Here's a function I've chosen. X minus 2 times x minus 3 times x minus 1. Now this last term, the 1 over here, I've set using this slider, so I can change the value of this one if I want to. Well, let's have a bit of a look. You can use the null factor law to find the x-intercepts or the solutions. So the x-intercepts will be when either this equals 0, so that equals 0 when x is 2. So there's that one right there, that intercept. For this one, that middle term will be 0 when x equals 3. So there that is, x equals 3. And this one will be when x equals 1. Now, so far it looks like the turning points are symmetrical, but that's only because of the values I've chosen here. So if I change a to, say, 0.5, so this term is x minus 0.5, now I've changed my intercept here to 0.5. Now if I change this to, say, 0, the intercept is 0, and if I change it to minus 0.5, the intercept is minus 0.5, because here we have x plus 0.5. So, and the further away I go, the clearer it is that these are actually, that it's not at all symmetrical like it was before. And I can keep going and going and going. Now, a couple of little interesting things we can do with this is ask the question, what happens when I make a to be 2? So here it is at 1. We're going to investigate if that one here was a 2, then this term would be the same as that term. In other words, what we're going to notice is the graph sort of squashing together, so this 1 and that 2 are sort of 1 point. So let's check that out. So there we go. So now it just sort of only just touches the 2 and then goes through the 3. And here it's written like this, but another way to express that would be, so for that particular example, it's x minus 2 squared, because we have 2 of them, times x minus 3. And that one we saw before. Now, a second little thing we can do, what happens if I shifted this 3 point so that it also was the same? So I'm going to squash this graph further, so it's the same there. I might add in a second slider to do this, I think. So I'll call it B. Okay, so I'll change this 3 over here to be that variable B that I just created. Alright, so B was at 3 initially. Now I'm going to shift that 3 so it's also at this point of 2 here. So it's getting closer, and there we go. So now the whole graph has sort of squashed to be around this point 2. So let me show you that again, so it's a bit more clear. So I'll move that point away from the 2, and I'll move this one away from the 2 as well. So here we've got sort of like the maximum and then a minimum, or like two turning points if you like. Now as I move this one closer to 2, so now it only crosses once, and now I'll move this one closer to 2 as well. And there we go. So now it's not really a turning point at all. All that's happening here, well, I may have 0 gradient, but it's actually a point of inflection. So what inflection means is here we've got basically just means it's a stationary point. So the gradient here is small, but then and slowly decreasing. The gradient is decreasing, and then past the point of inflection, the gradient is increasing and getting larger and larger. So, and we can write this equation as cubic. So let's show you how you can write this now. So this second one I've done would look like this: x minus 2 all to the power 3. And when that happens, this general shape has slightly changed to now it's a point of inflection. It's a point of inflection instead of having two turning points here and here. So the shape has sort of changed. So first let's consider this this most common shape, and then we'll come and consider how to do these points of inflection type later on. So first, with this type, the way to be able to sketch this is first make sure it's in factorized form. So I'll write a general one in factorized form. If we have x minus a, x minus b, and x minus, go away, and x minus c, then we can sketch it showing the three bits where it crosses the x-intercept as a, b, and c. So I can do a quick sketch of this, where one of the points is a, the next one will be b, and the last one will be c. You also need to show whatever the y-intercept is by putting in x equals 0 and solving for y. So in this particular case, it will be y will be negative a times negative b times negative c. So all the x's are 0. And here we've got three negative signs, so overall that's a negative, a times b times c. So that y-intercept here is minus ABC. So this one here, minus ABC, that y-intercept there. Okay, now an interesting thing is, let me sketch a different graph. Let me in fact change, let me change one of these, the coefficients in front of x to just be a negative. So make that negative, I'll make it negative 2, and let's change these back to the values they originally were at 1 and 3. So here we go, I've got negative 2x minus 2, x minus 3, x minus 1. And look what's happened. The graph has flipped over. Or maybe this 2 is unnecessary. Might be too confusing. Okay. So the graph has basically just flipped over there. Still got the same intercepts, but now it's coming from a large value and going down to a very, very small value. And why is that? Well, it's because now if we expand it out, so if we expanded that out, where there's a negative in front of one of the x's, it would mean when we expanded it, this a value here, that value of a, would then be negative, then be a negative value. So this is the shape if it's a positive value for a, but if it's a negative value for a, it sort of flips over. Whoops, that's a bit of a bad picture, but you know what I'm trying to say. It sort of flips over and reflects across the x-intercept. So that's really all you need to know. You need to be able to say is this term times this term times that term, all the x terms combined, is it going to be positive or negative? If it's positive, it's a graph like this. If it's negative, then it will be, negative 1 will be more like that. And then you need to find the intercepts and go A, B, C, and find the y-intercept. And then you're done. So that's how you graph those type. Now, how you graph these ones that are a point of inflection is slightly different. The way you have to do it is using our knowledge of translations, and reflections, and dilations. So this is quite very similar to using translations, reflections, and dilations with our quadratics. But here we'll start with, if we start with x cubed, then if we want to shift this graph up, we can add h, and that will shift it. That will shift up, so h shifts up. Then if we want to, we can put a minus k in there. The cubic's still there, and we'll leave all the things I've done. So that will actually shift it towards the right, this minus k value. So h units up, k units to the right. Now if I put a negative sign, that will reflect it. Minus k cubed plus h. So that's a reflection, it's sort of a flip. So reflected across the x-axis. And now if I put a number here, say a, I'll just change it to just a, x minus k cubed plus h, that is a dilation of a units. So if a units. So basically dilation, if a is a large number, it's becoming skinnier, more squashed. If a is a small number, a decimal number, the graph is becoming more spread out. So that's basically all the theory, and all this next is a couple of examples. So if you're feeling confident, you can just give this a go yourself. Otherwise, stick with us for an example or two. Okay, so here's our first example. We're asked to graph y equals 2x minus 1 times minus x minus 2 times x plus 3. So first, let's see if it's either going to be that shape or if it's going to be this shape. So to do that, we'll multiply all just the x terms together to get our like our ax cubed term sorted out. So we're going to have we've got 2x multiplied by negative x multiplied by x, and we see that that is going to be minus 2x cubed. So that's just this first term that we've done there, and because it's negative, we know that it's this second type, the inflected, the reflected type. So it's going to be that shape there. Okay, next we're going to find all of the x-intercepts, and then we're going to find the y-intercept as well. So first let's consider the x-intercepts. So the null factor law tells us that the x-intercepts are when either this first bit equals 0, so that'll be when x is a half, then this will be 0. So one of them is x is a half. The second one, when this is 0, is when x is equal to negative 2. Because negative of negative 2 is positive 2. Positive 2 minus 2 is 0. So x could be this one, negative 2. And for this one, it will be x will be negative 3 for this third bit to be 0. Negative 3. So those are our x-intercepts. Next, we need our y-intercept. So for our y-intercept, we'll set x equal to 0. Solve this for when x is 0. We get y is minus 1 times minus 2 times 3. So y is minus 1 times minus 2 is 2. 2 times 3 is 6. Y is 6. There we go. So we've got all the information, and now we are ready to sketch it. Okay, so labeling our axis, that's the y-axis, that's the x-axis. Put in all our information, so x is, could be a half, minus 2, or minus 3. Y-intercept is 6. And it's going to be this shape here. So it'll start high, it'll come through 3, go through 2, come up through 6 somehow, and back to through a half. So the only real difficult bit about this is to know, is the turning point sort of here and then it comes back through 6 on that side, or does it go through 6, keep going, and then come through minus a half? And for now, I'm not going to show you how to do that. The best way to do that is using calculus, using differentiation. The only way you can really do it is sort of using some trial and error and pick a point very, very close to the x-axis, very close to x being equal to 0, and see on which side, if it's going up or if it's higher than 6 or lower than 6. So on one side it should be higher than 6, one side it should be lower than 6. For this one, it's just going to be on here. So there we go, that's our first example, and that's all the information you need to show on your graph. Okay, now for our second example. Okay, so here's our second example. We're asked to sketch y equals half x minus 3 cubed minus 4. So we notice that this is one that's going to only have a point of inflection rather than several different x-intercepts. So let's see. First, we can find. So we know it's based off a graph that looks like this because our first term, A, is positive. So we'll have this shape. Now, we also know that it will be a little bit wider than usual because of this half. So it'll be sort of a little bit more sort of spread out, if you like, a bit fatter. Now, this minus 4 means that it'll be shifted down 4 units. And this minus 3 means it will be shifted towards the right 3 units as well. So, so it's going to be a point of inflection sort of, well, point of inflection. Doing a bit of a bad job of drawing these inflection ones. Point of inflection, shift down 4 and across 3. So let's make a bit of a start on this graph. X, Y. So down 4, across 3, 4 across 3. Let's say this can be the point of inflection. Let's say. So something along those lines. That should really come flat there. Okay, and we'll label this point as it's come across 3 and it's come down 4. So I've labelled the point of inflection. Now the only other two things we need to worry about are the y-intercept here and the x-intercept here. So first let's find the y-intercept. Doesn't matter which order you do this in. Y-intercept is when x equals 0. So sub x equals 0 into this equation. Y equals half of minus 3 cubed minus 4. So that's half times minus, because the negative sign will stay there for a cubic. 3 to the power 3 is 27 minus 4. So that gives us minus 27 on 2 minus, now I'm going to change this 4 into something with a denominator of 2, which is minus 8 on 2. So that will give us minus 35 on 2. And you can leave it in this form rather than writing that as 17.5. It's usually better to actually leave it as an improper fraction. Oops, 35 on 2 is the y-intercept. And now we've got the x-intercept. And the x-intercept is when y equals 0. Intercept is when y equals 0. So we've got half times x minus 3 cubed minus 4 equals 0. So it's a half minus 3 cubed equals 4 by putting this to the other side. Now we can multiply both by 2, getting x minus 3 cubed equals 8. Now I can do a cube root of both of these. X minus 3 equals the cube root of 8, and the cube root of 8 is 2. Now we'll add our 3 to both sides, x equals 5. So this point here is 5. And then we've labelled all of the different things, and we've shown the orientation of our graph as well. So we're finished. So there we go, best of luck, and I'll see you in class.